Hey guys, welcome. We're going to do the multiple choice for 7-2 and we're going to use our notes while we do it. Okay. So just a review, we did a Reese's Pieces activity, or we started it, right? And we noticed it is binomial because it's either orange or not orange. We decided to pick 50 candies, so we have a set number, and we are told that 40% are supposed to be orange. So notice, we also kind of brought in this 10% rule that even though we're not replacing the candies, it's a really, really, really big machine. And as long as there is enough, it should be okay that we're not replacing it. Okay. So we made this dot plot and we said, okay, there's nothing surprising here. 40% of 50 is 20. So if we picked 50 candies, we would expect 20 out of the 50 to be orange because they said 40% are orange, right? So that's why we got a lot of 20s, but we also got quite a few more than 20 or less than 20 because of this idea of variability, right? So back to, how do I find the mean of this distribution? Well, if I have 50 and I'm expecting 40%, then I'm expecting the average or the typical value here would be 20, right? We also know that a certain amount of variability would also be reasonable. So using this formula, if I have 50 and I'm expecting 40% to be orange and 60% to not be orange, right? Then that would mean I'm expecting about 20 candies to be orange out of the 50, or up to about 23.5 candies. Those would be reason. Most of the samples would be up to 23.5, or 20 minus 3.5, right? Somewhere around 16.5 candies. And that was true as well. Most of the samples fell between 16 or 16.5 and 23.5 or 24, right? Most of our samples fell within this range. So notice we can actually quantify what we should expect and the variability of what we should expect, okay? So taking a look at our problem here, it says, let's see if we have all of our components. We took a random sample and it was 750. And we're supposed to suppose that our proportion is 30%, right? And they want us to calculate a sample proportion. So we are definitely taking a sample, right? So what we could expect the mean to be. So we know that the mean would be, okay, well, it's just N times P, right? We talked to 750 and 30% of them should say that they believe drugs are a problem. And then what would be this standard deviation? Well, that would be this formula we used in our notes, right? And I get 12.5. Now there's something else though, and this is where we were going in our notes before we had to stop. It's actually not asking for the sampling distribution of the sample, but the sample proportion. So this is a different request here. So that takes us to the next page of our notes. This is where we're going to do a proportion. And so we notice that the dots are exactly the same. In fact, I actually copied the dots from here and put it here. So the only thing that changes is our number line, right? So the 20 out of 50 is now a proportion. So that would just be 40%. So again, we're expecting 40%. But we might expect a little more than 40% to say that are orange, right? Up to 3.5. Oh, out of the 50. So it'd be 20 plus another 3.5 orange out of the 50, or 20 minus 3.5 orange out of the 50. So notice how the proportion also creates the same graph, and it just changes the x-axis. So since they asked for the proportion, and just like we did in our example, we're going to just divide by n. Here, well, what would be our mean proportion? It'd be, I'm expecting 225 out of the 750. Now I have a proportion. What would be my standard deviation proportion? It would be, I'm expecting 12 and a half more than 225 or 12 and a half less than 225 out of the 750 I asked. So now we have our answer. This merely goes back to the 30%. So we get our answer here. So these are the mean proportion and standard deviation proportion of our sample. Now let's look at this stuff algebraically. So what happened here? Well, our mean was in times p, but our mean proportion, we had to divide by n again to create a proportion. So notice how that makes sense algebraically. We just got back to the b. So the mean of a sample proportion is just whatever your p is, your proportion of the population. Let's see what happens with our standard deviation. So the standard deviation was n times p times 1 minus p, take the square root of the whole thing, right? And if I turned it into a proportion, I divided by n. Now, it might not seem obvious to you, but I have like terms here. So in a formula book, the standard deviation of proportion wouldn't look like that. Just like we canceled this, we can do some canceling here. Now, you don't have to know this because the formula will actually tell you, but you'll be wondering like, well, why is that formula different? All right, so I'm going to break apart that, and we notice that, let's just put numbers to this. If you had the square root of 2 over 2, you wouldn't, you could leave your answer like that. But we could actually make this a little bit nicer and get everything under the square root. What I mean by that is, this could also be written like this. You're saying, oh, what do you mean? Well, remember, back in the day, if you had an answer like this, you would rewrite it like that. So I've just kind of gone backwards. If this is the square root of n over n, I could have just wrote it the square root of n. And now, notice, my formula is actually the standard deviation of a proportion would actually be written p times 1 minus p all over n, and I take the square root of the whole thing. And so that's how you'll see the formula on the formula sheet. And again, I got the same answer the same way. So if you use the formula off the formula sheet, you would have still gotten 0.017. Okay, enough of that. Most of the time, you're just going to use the formula, but that's why the formula is like that. Okay, so using our formula, we've established this. How would the standard deviation change? Well, we know from our notes, when we increase our sample size, the standard deviation decreases. So the opposite would happen. When I decrease my sample size, right? So I decrease it. It looks like this is cut in half, right? 750 divided by 2 is 375. When I decrease our sample size, my standard deviation would increase. So that's why they're saying it increased by a factor of how much, okay? So if we look at, I have a standard deviation before, and I'm going to multiply it by some type of factor to create my standard deviation after. So taking a look, what is my standard deviation formula? Well, we just created kind of a new one. It's p times 1 minus p all over n, take the square root of the whole thing. And the same thing for this one, right? The difference is that n is different on either side. So let's take a look there, right? Our proportion is the same. I think it's 30%, right? But here n is, before it's 750. And here it's 375. Now, I can break this apart. Let's see. I could take the square root at the top and the square root of the bottom. Same thing here. And notice I have that square root of p times 1 minus p on both sides. So that can actually be canceled. If I divide both sides by that quantity, it would go away. So now I want to get x by itself on one side, right? So I can take this and move it up here. It's kind of the swap, right? The butterfly swap. So we have the square root of 750 over the square root of 375. This can be combined as one quantity. And we get the square root of 2. Okay, so that makes sense. That's our answer, the square root of 2. And if we turn that into a decimal, it's 1.4. So when we decrease our sample size, or when we cut the sample size in half, we know that our standard deviation would increase. Now, it won't increase by double, but it would increase by a factor of 1.4 or the square root of 2, which kind of makes sense. Okay. Now, 55, the sample distribution of p hat is approximately normal because. So we talked about that in our notes as well. We noticed that we literally saw how this graph, step by step, did not look exactly normal when n was smaller, and eventually as n increased and increased and increased, it shaded this in and it made a very nice looking approximately normal shade. So when did we know in our observations when it became approximately normal? It seems it's approaching it. And through observation, we didn't actually completely observe this, but we somewhat did, is that when we have successes and failures of at least 10, so when they are 10 or more, and we more than had that. And what I mean by that is, notice that if we had a sample size of 50, and we ended up 40% were going to be orange, so we're expecting 20 of the 50 to be orange, which is what we're calling success, then we would expect 30 to be not orange. And both of those numbers are greater than 10. And so that's why, meaning our sample size was large enough that our distribution would be approximately normal. All right, so back here, this is saying the same thing. If we talk to 750 people, right, then 750 people times 30% would say yes. We would get 225. We're expecting 225 to say yes. Drugs are a problem in our sport. And that would also mean you would expect 525 to say that it's not a problem. And notice this is more than enough people. We talked to lots of people, right? Because we noticed that this is much greater than 10, and that's much greater than 10, and that's why the distribution would be approximately normal, because both of these numbers are at least 10. So this is our answer here, B. All right, 56. In a congressional district, 55% of the registered voters are Democrat. Which of the following is equivalent to the probability of getting less than 50? Okay, so we kind of alluded to this, that we can actually start using the sampling distributions that we have to actually do calculations of probability like we did from back in chapter 2. So we have a mean and a standard deviation, and we know that your mean from your sample would be just your P, right? If that is all 55% of all those registered in this district are Democrats. And what is our standard deviation? Again, the standard deviation of our sample, all right? Standard deviation of our sample, we said, is the square root of the whole thing, P times 1 minus P over N, because we cleaned up that formula. So let's see what that would be. So our mean of our sample proportion is just P, and our standard deviation of our sample proportion is P, 1 minus P, all over N. So that's 0.3, 0.7, all over 100. Nice. Now it looks like here I don't actually have to calculate it. I can leave it without putting it in the calculator, but that's going to be my standard deviation. So how would I use what I've learned here and what I've learned back in chapter 2. Well, I know my mean. I'm expecting 55% Democrat. But what's the probability of getting less than 50%? So that would be here. So again, they're asking what's the area under the curve to the left because they said less than. So this is our z-score, right? Z is equal to A minus P over S. Actually, what did we actually get? 50%. What we predict to get, that would be our mean, 55%, over our standard deviation, which is the square root of P, 1 minus P, over 100. Now, did I use... Oh, excuse me. I'm using my P. I swapped my P. You guys were probably totally confused this whole time. Where did that come from? Right? Again, my probability is 55 in this problem. And so 1 minus P over 100. I was squishing my data from the last question. They switched data on me, right? P, 1 minus P, right? So what will we have here? P, 1 minus P over N. And I need Z to be less than that, right? So here is our formula that's matching what we're coming up with. Perfect. Nice job, guys. See you